Hello, and thanks for tuning in to my talk, Securing Container Delivery with TUF. My name is Lukas Puehringer, and I'm a software engineer and researcher at New York University's Secure Systems Lab, which is led by Professor Justin Kapos. I'm recording this talk today in my hometown, Vienna in Austria. And although I would have really liked to give the talk in Amsterdam and meet some of my colleagues from New York and from the rest of the world, I'm really happy that I can still present today remotely. And given that I work from Austria for a United States university, I'm somewhat used to working remotely. And sometimes I even get help from my newborn son. My work deals with software supply chain security. In the past 4 years, Professor Kapos and Santiago Torres, who recently received his PhD degree for our work, we created a software supply chain security framework in Todo. In Todo is just as TUF hosted within the CNCF, and just as TUF in Todo makes sure that the software you install is the software you actually want to install and not a tempered version of it. In Todo does so by creating a verifiable trace from the first lines of code until deployment or installation. And TUF takes care of the delivery. So the real difference between those two frameworks is the region, the supply chain where they operate on. Today we're going to look at TUF. As I said, TUF takes care of delivery, so that the software comes to the client. The client may be a person who installs a binary package from his or her programming language package manager, but it can also be a server that deploys a containerized image for production. So TUF really works with any existing infrastructure. It's really, to put it in a very simplified way, it's really just a bunch of metadata files and cryptographic keys and the knowledge how to modify those files and sign them on the server and how to interpret and verify them on the client. But we'll talk more about this later. I want to take a step back first because the story usually doesn't end with installing software once on a client. You also want to keep it up to date. And as the name of TUF suggests, this is what we're interested in. But why do we care about updates? Updates don't only allow us to roll out new features and use new nice hardware. It also updates. It also fixes security issues and bugs. So updates by itself is very important for security. I have an example here where a recent iOS update fixes a quite scary privilege escalation vulnerability. And this is also why security experts agree that one of the most important things that you can do to keep your infrastructure safe is to always keep software and systems up to date. On the other hand, the update infrastructure is also a very attractive target for attackers because a single successful compromise can have impact or can affect thousands and millions of end users, be it users who install apps on smartphones, on their desktop computers, or as I said earlier, on a production server. So these things not only happen in theory. Here's a little list of platforms and products who all had their publishing infrastructure compromised. The effects were varying, but I just want to show that these things do happen. So we do need to have a plan B for when a compromise happens. A very natural approach for many would be to just sign it. There are a couple of common approaches. One would be to sign the communication channel using transport layer security, which is really great for protecting against man-in-the-middle attacks. But the problem is that TLS heavily relies on a single key. So if an attacker breaks into the server, then they can serve you whatever they want, albeit over a secure channel. Another approach that does involve offline keys is GPG. GPG has the problem of distribution and revocation of keys. So even if you regularly go to key signing parties, which I'm sure you all do, then how do you know which key is authorized to provide signatures for which package? And how do you encode such things as signature thresholds, where you want multiple signatures from different keys to provide guarantee for a package? So GPG has a couple of usability problems. There is even research about this. So no, we can't just sign it. We need a little bit more than cryptographic signatures. And TUF offers that bit more. TUF does not only protect against a wide range of attacks, it also reduces the impact for when a compromise happens, and it allows you to recover from it. And this is really what distinguishes TUF from other protective measures, the compromise resilience. Let's take a quick look at how TUF does this. So it follows a couple of principles. For instance, it separates responsibilities. You have different keys for different responsibilities. So if one key is compromised, then not the entire operation is jeopardized. Separating responsibilities also allows us to give different weights to different responsibilities. For instance, high impact responsibilities get very secure offline keys. On the other hand, if we need online keys, for instance, due to availability concerns, then we give them low impact responsibilities. Another mitigation technique to reduce the impact of a compromise are signature thresholds. I mentioned this earlier when I talked about GPG. It's a little bit like having different keys for different responsibilities. Even within one responsibility, we can encode thresholds in TUF to say, for this responsibilities, I want n different signatures from different keys. So these are all techniques to mitigate the impact of a compromise. And another thing that TUF has built in its core design is the way to recover from a compromise. When a key is lost or stolen, we need a way to tell our clients to not use that key anymore and instead use a different one. And TUF has ways to do explicit and implicit key revocation. We'll talk about that in a minute. Let's first talk a little bit more about those responsibilities I'm mentioning all the time. So TUF responsibilities, or roles as we call them, there are 4 of them. There is the targets role, which takes care of the integrity of target files. In TUF jargon, we call target files the application binaries or container images or any file really that we are interested in, that we want to update. And there is a specific role for that that's dedicated to guarantee their integrity. Then there is the snapshot role, taking care of consistency of the overall repository, the timestamp role, taking care of freshness, and a root role that takes care, or that serves as the root of trust for all of these roles. These roles all probably look nice and reasonable, but also quite abstract. At least when I first started to work on TUF, it was hard for me to extrapolate to how this really looks in code and in an implementation. I already said this earlier, that it's just a bunch of metadata files, and in a very oversimplified way, this is true. So for each of these roles in TUF, you have a specific metadata file. For the targets file, you have targets metadata. For the targets role, you have targets metadata. For the snapshot role, you have snapshot metadata, and so on. In the case of targets, in the targets role, there can be more than one metadata files, but for the others, there is usually only one. Let's look at each of those files and see what they contain and how they protect the software update infrastructure. First, let's take the targets metadata. Targets metadata is responsible for the integrity of target files. I said this earlier. It does so by listing each of the target files on the repository. For instance, here in this example, we have a Python package, Beautiful Soup, which helps you to parse HTML pages. And to protect its integrity, it lists its hash. So when you download that package, you can compare it to the hash in the metadata and know if it's the benign package or a tampered version of it. This protects you against, or this is called an arbitrary software attack, where an attacker just replaces the package with a malicious one. This is probably the most scary attack. The targets metadata also has a length field for each of the target files. This protects against endless data attacks, where an attacker breaks into the repository and serves the client a really huge file to crash their hard disk, for instance. Next, we have the snapshot metadata. Snapshot is responsible for consistency of targets metadata and thus for target files. Here we only have, or it does so by listing the latest version of the target's metadata in the repository. In this example, we only have one target's metadata file listed here, but usually, or in real world, there are often more targets metadata files to encode complex trust delegations, which are a bit out of scope for this talk. But having all these targets metadata files, an attacker won't be able to serve an inconsistent state, even with maybe benign different versions of packages that together break the client. So that's a mix and match attack. Then we have the timestamp metadata. Timestamp metadata is responsible for the freshness of snapshot metadata and thus targets metadata and thus target files. It does so by always listing the latest version of snapshot metadata on the repository and also having a very short expiration period. This is called implicit revocation because the client will regularly discard old timestamp metadata and request new one. So a client won't be able to launch a freeze attack where an attacker won't be able to launch a freeze attack where they trick the client or make the client believe that there are no more updates. And as we saw earlier in this slide about the iOS update, all software is often vulnerable software. So it's important to always keep our client, to always inform our client about new updates. A similar attack is the rollback attack. Timestamp uses a version number for itself to protect against that. That's when an attacker serves an older metadata file than the current one that might not have yet been expired. And to protect against that, we have a strictly incrementing version number in timestamp, and also in the other metadata files for redundancy. I left this out to keep it brief and simple here. But the idea is to only allow higher version numbers whenever we update a metadata file. And last but not least, we have the root metadata file. It serves as root of trust. It has a built-in public key store. That means it lists all the keys that are used for signing metadata in a TUF-enabled system. Only the public portions of those asymmetric keys, of course. And the client can use these keys to verify the metadata. It furthermore lists, it has an entry for each of the roles. Here I only show targets role, but it also has an entry for snapshot, timestamp, and root itself, where it maps the keys from the key store to the role by an ID. And it also defines a signature threshold. So for instance, in this example, we require at least 2 valid signatures for targets metadata using any of the key IDs defined here. So if a key is compromised, and we talked about this earlier, this happens. If a key is compromised, then we just need to update the root metadata, add a new key to it, to the key store, and replace the assignment in the role entry. So here we just remove the old key ID that's authorized to provide signatures for the targets role and add the ID of the new key. This is called explicit revocation. This even works for the root metadata itself. It's a little bit more complicated, but you can also just rotate the keys that root defines for itself. So this is basically it. That's the core concepts of TUF. If this all sounds very complicated, you don't need to worry because there is extensive tooling. We at New York University host a reference implementation that's written in Python. And it's also used in production at Datadog. And then there are plenty of other implementations in other languages that are used for other TUF adoptions. There is an implementation in Rust. There is an implementation in Go. I think there's also one in OCaml. And yeah, they are used by various organizations to secure their updates. AWS, for instance, just released their Bottle Rocket OS earlier this year, which is based on TUF. Google Fuchsia also uses TUF concepts under the hood. Then there is Notary v2 that's protecting container images. Well, there is Notary, and Notary v2 is currently being designed. There is also a fork of TUF, which is called Obtain, and it's used widely in the automotive industry to protect updates of computer components in cars. And one work in progress adoption I'd like to point out in particular, because we at NYU are heavily involved in making this happen, is PEP 458. That's a standards document that describes how to use TUF with the Python package index. And we, the Python Software Foundation has received funds to make this happen. And we at NYU are helping to update our reference implementation, which somehow forces us to revise some of our concepts and add a couple of usability enhancements and also performance optimizations, which is really great. And we're also adding new exciting features to our reference implementation, such as the ability to sign with hardware security modules or using cloud storage for metadata and so on. If you want to learn more about TUF, feel free to visit our website, theupdateframework.io. There are links to the specification. Are also links to the software source code repository on GitHub. It's all open source what we do. Please also sign up to our mailing list. It's very low traffic, but we announce our monthly community meetings there, where everyone who's interested in TUF or thinks that TUF might be a good addition to their infrastructure is welcome to join. I'd like to thank you for tuning in again. I'd also like to thank my colleagues for working with me on this. In particular, I'd like to thank Joshua Locke from VMware, who has been a lot of help lately in making enhancements to the reference implementation of TUF. I'd also like to make a quick announcement that Santiago Torres will be giving a talk about Intodo in an hour here in Virtual KubeCon. So make sure to check that out too. And yeah, stick around for the virtual Q&A and talk to you in a bit. Thank you.